or in short, DOE. Outlines for this particular topic. What I'm going to cover is basically I'm going to introduce the concept of a DOE. What is the concept? What is the purpose? And what can you do with it? And then we're going to look into how to design the design of experiment. So before you conduct any experiment, you have to design it first. You have to know what data to collect and what to do with the data before or prior to running the experiment itself. So it's very important for you to be able to design the experiment before you execute it and collect data. If not, then more often than not, once you get your data, then you have no idea on how to analyze the data and what information you can extract from those data. So basically, this is very, very important, and I've encountered many issues with regards to students coming to me, showing me a set of data and ask me, how to analyze it. So you have to design it first, so that you know what data to collect, how to analyze, and what conclusion can you make out of the analysis. And after that, we're going to go through some simple examples. I do not intend to teach you step by step on how to carry out DOE, but I would like to introduce you the concept and give you some examples on what you can do with the DOE. So if this particular method is suitable for your research application, then you can do more readings or you can contact me, then I can advise you on what to be done, right? Because not all experiments or not all research should utilize this type of experiment. You can use other methods. But for this particular case, we get to concentrate on design of experiment. And I'm also going to show you a case study, one examples on what this type of experiment can do. We're going to go through a simple examples of a DOE. Uh, it's not going to be complicated, but I'm going to show to you the extent of information that you can gather from DOE, but I won't go into details step by step, so that you can appreciate the power of these particular tools. As an introduction, let me touch a bit on the two applied scientific experimental methods that you can use. So in scientific experimental methods, in general, you can classify it into two methods. One is called passive observation methods, and the other one is called active observation methods. So basically, passive observation method is when the experiment is only an observer of the nature's processes and the experimenter does not interfere in the environment. The experiment has no control over what the events and the outcome, and cause and effect relationship are obscured by uncontrolled variables and multiple unrecorded causes. So this is passive observation methods. So in summary, the passive observation methods is methods where you actually observe what happened. You do not interfere. You do not control the parameter. You just observe what happened in the natural environment, and then you collect data. And based on the data that you collect, then you come up with a cause and effect relationship. Um and basically the cause and effect relationship is controlled by variables that's not within your control, right? So basically but you have to explain the cause and effect relationship with regards to these uncontrolled variables. Example of this is, for example, if you are doing, let's say for example, you're doing a research in terms of observation of the tiger population behavior in the jungle. right? So what you do is just you observe, collect data, and then at the end of it, you come up with conclusions in terms of cause and effect relationship. For example, the tiger is more active at night compared daytime. You cannot change the variables day and night. What you can do is just observe, collect data in terms of the activeness of the tiger at night and daytime, and based on numerous data that you collected, then you make conclusions, right? So that's considered passive observation methods, right? The other methods under the scientific experimental methods is called active observation method. So in active observation method, the experimenter has partial or complete control of the environment. So in active observation method, then basically you as the experimenter has partial or complete control of the environment. So for example, if you want to observe, you want to do the experiment, how does the temperature, oven temperature affect the softness of the bread that you bake, for example, right? So you have the capability to control the temperature. We control the environment. So in that particular case, the experimenter has a partial or complete control of the environment. Why it says partial? Because there are some factor in baking that you cannot control. For example, humidity of the room. Maybe you cannot control the humidity of the room. So you can only control the temperature of the oven, and you don't know whether humidity of the room will affect the softness of your bread or not. So that's why you say that partial or complete control of environment. Deliberate changes are induced in the environment. The goal is to find cause and effect relationship. So in the active observation methods, basically you induce the change in the environment. For example, you change the temperature, so you in one experiment you bake the bread at 150 degree Celsius, and then the next set of experiment you run it at 180 degrees Celsius, and you want to find the cause and effect, what happened to the softness of the bread as you increase the temperature from 150 to 180 degrees Celsius. So that's what meant here. You deliberately change the environment, and you're going to explain the cause and effect relationship. The results are reproducible, simplifying models used to understand the complex relationship. So results are reproducible, meaning that you should be able to repeat the same experiment with the and get the same result. Yeah. So let's say, for example, today I'm going to run the experiment of baking a cake at different temperature. So at 150 degrees Celsius and 180 degrees Celsius, my results say that the bake is much softer at 180 degrees Celsius, right? So tomorrow I should be able to reproduce those experiments. No, I should be able to reproduce it. So care must be taken in terms of the methods of running the experiment and keeping notes of what happening during the setup of the experiment, so on and so forth, so that you can reproduce the experiment. And simplifying models used to understand complex relationship, and based on those data, then you can actually come up with a model. It can be mathematical models that explain the relationship between the temperature and the softness of the bread in our example just now, right? So when you run this kind of experiment, active observation methods, you change the parameter that you want to know the effect on the output response. So just now the parameter is the temperature, and the output response is the softness of the bread, right? So you run the experiment, you collect all the data, and you come up with a relationship between the two, between the temperature and the softness of the bread. And based on the data you collect, you actually can come up with a model, mathematical model, to explain the relationship between the temperature and the softness of the bread. So DOE, design of experiment, falls under the active observation methods, right? So from now onwards, what we're going to do is basically we're going to talk about design of in the active observation methods. Basically, there are many methods that can be used for those experimentation mode. So I'm listing some of it. So this is methods of experimentations. The first method that sometimes people use is trial and error methods. Uh, Sorry. So trial and error methods basically treat the symptoms, look for quick fix, and make random changes to process variable. So in trial and error methods, basically, if you're facing, usually if people facing issue or they want to improve they say, for example, we take an example as we have just now, the softness of the cake, right? So you want to improve the softness of the bread. So in trial and error method, basically, if let's say one day when you bake a cake and all of a sudden the cake become hard, so you want to fix it. So what you do is you treat the symptoms, and based on your experience, you say that, okay, I'm going to reduce the number of flour that I'm going to, that the inside as the ingredient of the bread, right? So you try to reduce number of flour by maybe 10% and bake the cake, and you find out that by reducing the flour it didn't fix it. So next what you do is maybe you try to both reduce the flour and also increase the number of egg, for example, and then you bake the bread and see the result. So those are examples of trial and error methods. And in formal experimentations, in research, you shouldn't do this. Even in industry, if you work in industry, you shouldn't do this. Because it's going to be very hard for you to come up with the conclusions with a good statistical data to back up your conclusions and decisions in changing the parameters. So this is trial and error method, and you shouldn't use it, right? The other methods that people used is one factor at a time method, OFAT. In this particular method, you vary one factor while holding other constant. Does not consider, but this method does not considering the combined effect of variables. So if you are doing an experiment and purposely you want to look at the effect of parameter only, like baking a bread, you want to look at the effect of temperature versus softness, and you don't have any intention to look at other parameters, for example, number of eggs, amount of flour, so on and so forth. No, you don't want to change that, and the only objective of your experiment is to understand the effect of temperature with respect to the softness of the bread. Then by all means you can use this one factor of the time approach. You change the temperature at let's say, for example, three different levels. Temperature at 100 degrees Celsius, 150 degrees Celsius, 180 degrees Celsius, and then you bake the cake at those temperatures and observe and collect data in terms of the softness of the bread. So you can do that. It's not an issue. It's not an issue. But if your intention is actually to look at more than one variables at a given time, let's say, for example, you want to look at, let's say, for example, the effect of temperature and also the effect of number of eggs to the softness of the bread, then you should not use one factor at a time. You should use other methods, which is full factorial or fractional factorial design experiment. Because if you want to find out the effect of two variables at a time, but you are running one experiment, you just run the temperature at three different levels and look at the softness of the bread. And then the next set of experiment, you change the number of eggs and look at the softness of the egg. What going to happen is you are going to lose the opportunity to understand the combined effect of eggs and temperature. That's what it means. Does not one factor of the time doesn't consider combined effect of variables. So again, if you want to find out the effect of two parameters, two variables on the softness of the bread, for example, if you run it one factor at a time experiment, then you're going to lose the opportunity to understand the combined effect of temperature and X. So if you have intention to find out the effect of two variables, more than one variables during that experiment, then don't do one factor at a time. Huh? Okay, that's bring me to the next methods of experiment, full factorial design of experiment. Full factorial design experiment examine all combinations of variables and look at the combined effect of variables. So if you have more than one variables, two, three, four, five variables, and you want to find out the effect of those variables to the let's say softness of the bread, then basically use the full factorial design experiment approach, because it actually will tell you the effect of each variables to the softness of the bread, and it will tell you the combined effect of the variable to the softness of the egg. So this is called interaction factor. So it will tell you the interaction effect between various variables to the softness of the egg. Because sometimes in some processes, you know, the behavior of the process will change with respect to the combined effect of two variables. You know. Let's say, for example, at the softness, the let's say, for example, if you bake the cake at 150 degrees Celsius, right, and you change the egg from two egg to three eggs, right, the softness of the egg might increase, right? But if you run uh, bake the cake at 180 degrees and you vary the egg one from one egg to two eggs, maybe the softness of the egg will decrease. So when that happens, then basically you have a combined effect of variables. So there's interaction between temperature and eggs. So because of that, then you need to understand to optimize your setting. The other methods that you can use, experimental method that you can use, is called fractional factorial methods. Fractional factorial design of experiment. It looks at the fractions of the possible combination, and usually use this for screening, getting preliminary informations, and look at the combined effect of variables, yield less information than full factorial. So let's say, for example, if you have a lot of variables that you want to study. Let's say we have 10 variables, right? If you want to run all 10 variables using a full factorial DOE, number of experimentations that you have to conduct will be very, very high, right? And out of that 10, maybe only four is are significant in terms of affecting the output response, right? So maybe you want to study, let's say, for example, amount of sugar, flour, egg, yeast, temperature, what else? Milk, humidity, so on and so forth, right? But out of those parameters, maybe only three parameters is actually important, significant in terms of controlling or affecting the softness of the egg, right? and you don't know which one. So what you can do, you can actually run fractional factorial. And in fractional factorial design experiment, what it does is basically it will reduce the number of experimentations that you need to run significantly, but you're going to get less information out of it. But you're going to get information with respect to which variables are important, which variables are important. But you might be missing the informations about the interaction factor, combined effect of variables. So it will tell you fractional factorial DOE will tell you which are the important parameters out of the seven, let's say, parameters that you run. So what you can do then is select the top three significant parameters, three or four, and then run full factorial design of experiment and get all the information with regards to the effect of the variables to output response and also the effect of the combined effect of the variables to the output response. So you can have two stages of experiment. One is the first one, you run the fractional factorial design of experiment. You assess the impact of seven parameters, and after that, then you get the data where it will tell you the top, let's say, for example, four significant parameters, and you choose that four significant parameters and run full factorial design experiment. And basically then you can have all the informations with regards to the effect of the each variables to the output response and also the combined effect of each variables to the output response. So basically, these are the some of the methods that you can choose in running an experiment. Uh, don't use the trial and error method. If you have one factor only to be evaluated in your experiment, by all means, you can use one factor at a time. But if you have more than one variables, then use full factorial design experiment to conduct your experiment. Um, and you can have two stages of experiment if you have too many variables. So you can do screening using fractional factorial methods. You reduce from 7 or 10 parameters to maybe 4 parameters, and you run full factorial design of experiment. Let's look into the definitions of design of experiment. So, design of experiment is one of the most powerful techniques for improving quality and productivity. So, if your particular project has something to do to improve something, either quality, productivity, yield, whatever it is, uh, then basically you want to consider to use design of experiment as your approach to that particular research. And definitions of design of experiment is basically a structured experimental strategy. So it's a very structured experimental strategy. It tells you if you specify what are you looking for, meaning that what variables that you want to study and what output you want to get out of the study. Then basically, design of experiment can help you to structure the experiment, meaning that it will tell you what are the experiment that you need to run, the first experiment, second, third, fourth, so on and so forth, and how to analyze your data and what conclusions you can get out of that particular experiment. So it's a very structured experimental strategy that allows for the simultaneous evaluations of processing variables. So again, as mentioned earlier, if you're thinking about evaluating multiple variables, multiple input variables, for example, in the case of baking a bread just now, so if you want to look at the impact of what do you call it, temperature, eggs, number of flour, baking time, then those are the variables, input variables to the baking process. So if you're looking to evaluate multiple variables at the same time, then you can do the experiment that actually simultaneously evaluate those processing variables on their ability to influence a product or process characteristic. So the structured experimental strategy that will allow you to evaluate simultaneously multiple processing variables on their ability to influence the product or the process characteristic. For example, in the case of baking bread just now, the softness of the bread. So X would be the input variables such as temperature, oven temperature, number of eggs, amount of flour, baking time, so on and so forth. And Y is the output response to that particular experiment. And in that particular examples of baking a bread, it could be the softness of the bread. Huh? And why the output of the experiment or product or process characteristic can be many. I mean, you can have more than one output responses. For example, if you want to look at the impact of the input variable X to the softness of the bread, to the color of the bread, to the, let's say for example, taste of the bread, you can do that. And basically you can run one experiment and have a multiple up response. And basically the experiment, the DOE will tell you what are the process parameter to be used that will optimize the taste, the softness, and the color of the bread. So that's what DOE is all about. It's a structured experimental strategy that allow you to simultaneously evaluate multiple variables, input variables of a particular process on their ability to influence the output responses of that particular process. And you can have multiple output responses. Let's look at the objectives of the DOE. So this can be like a checklist for you. They say, for example, if you want to do a research, and you can see whether this covers some of your research objective or not. If it covers, then maybe you can use a design of experiment as the approach of your research project. So DOE is useful to do these things. One is to identify the important factors, determine the variables that and their magnitude that influences the response. So it can tell you, let's say for example, if you evaluate four variables, for example, in our case of baking a bread just now, we're talking about temperature, baking time, baking temperature, number of eggs, number of flour, amount of flour. So basically, it will tell you which one is the most significant factor that influence the softness of the bread. Is it temperature? Is it the eggs? So on and so forth. So it determines the variables and their magnitude that influence the responses. So if it's aligned with the part of your objective of your research, then DOE might be a good approach for your research. Second is establish process stability. Determine how to manipulate these variables to control the response. So another side of DOE objective is to establish process stability, meaning that based on the output response, based on the data that you collect, you can analyze it, and based on the analysis, then it will tell you at what particular setting, what particular variables settings that the process would be stable. For example, in the case of baking the bread just now, right? So the result can tell you, for example, if you bake the bread at 150 degrees Celsius, any changes, any slight changes in the amount of flour will affect the softness of the bread. However, if you set your temperature at 180 degrees Celsius, uh, the changes in the amount of flour will not affect the softness of the bread. So that kind of information can be extracted from the analysis of the DOE. So this can be very powerful, especially if you want to set up a process, be it in your research or at your working place, and you want to have stability in terms of the output response with a slight variations in other variables. Right? So this is the second objective that you can that DOE can accomplish. Third is find the best operating conditions. So this is optimizations. So using DOE, basically this is an experiment, especially when if you use higher level order DOE, for example, full factorial and also or RSM, response-based methodology, then it can tell you what is the best operating conditions to achieve certain output response. For example, in our example just now, how to what is the variable should be in terms of amount of flour, number of eggs, baking temperature, in order to achieve the softest bread possible within that operating window. So it will tell you what's the best operating conditions. So this can be a guideline for you to check upon your research objective. So if your research objective has something to do with optimizations of parameters, with establishing a process stability, with identifying what factors are important and how that factor influences the output responses, then basically design of experiment is a very good tool for you to use for your research. This is the laundry list of DOE applications, meaning that where you can apply design of experiment. So you can take a look at it, see whether it match with your research area or not. But the application of a DOE in general is quite wide. You can go from the general applications, so you can look at it, product and process design. So if you want to design a process or design a product, then you can use a DOE. You can also use a DOE to look at the measurements, to do some analysis in terms of measurements. So if you want to compare different devices in the labs and see how how accurate or how they perform compared to each other, then you use DOE. Or in services, in service industry. So you can also use design of experiment in service industry. For example, if you want to evaluate the performance of workers during day and night, or during different shifts, at different education levels, so on and so forth. So you can use design of experiment to study those scenario. Or if you're in manufacturing, if you're in manufacturing, you want to look at the improving quality of a particular process or product, then you can use design of experiment for that. And even in marketing, if you want to look at customer preferences towards certain product feature, so on and so forth, you can use a design of experiment for it. For example, if you are in the area of looking at customer acceptance to, let's say, handphone, and you want to look at how customer acceptance in terms of handphone color, the color of the handphone. So you can devise and expand. You can design an experiment using DOE and assess which particular variables that actually affect the acceptance levels of the customer. So basically, a DOE application is wide, as long as the objective just now, in terms of you want to understand the variables and which variables and its magnitude uh, that impact certain output response, then basically you can use design of experiment as an approach of your research. Okay, let's look at the steps to experimentations. So these are the steps that you need to do before you can conduct the experiment. The first step that you need to do is actually to establish objective. So the objective of the research, the objective of the experimentation must be very, very clear to you. Uh, uh, what do you want to maximize or minimize during the experiment? For example, the example that we talked about just now about baking bread, right? So maybe you want to maximize the softness of the bread, or you want to minimize the crust of the bread. So whatever the experimentation that you do, you have to be very clear in terms of objective. And usually come with objective is either you want to minimize something or maximize something. Okay. So the second step is identify the factors and levels. So, so what factors and levels are known to affect the ability to minimize, maximize, or make things more consistent, right? So, you whatever process that you have to identify these factors and level. For example, in the examples of baking the bread just now, right? So the factor could be the temperature, and the levels for the temperature could be 150 degrees Celsius, 180 degrees Celsius, and 210 degrees Celsius. So this is examples of what factor and what levels are. So another factor that might be in the baking of the bread experiment, it could be number of eggs. So the factor is number of eggs. The level is one egg, two egg, three eggs, so on and so forth. So you have to know what are the factors that influence the objective, the process, right? And you can find it from literature review, from your experience, so on and so forth, right? So you have to read the published articles on that particular process and identify what are the levels and the factors and the level for that particular process. Brainstorm other factors. Brainstorm what other factors could possibly affect the objective. So another thing that you can do is you can brainstorm of factors that could possibly affect the objective. So you can talk to the expert in that particular process, field, so on and so forth, and identify the factors and the levels that could affect the objective. So once you know what's your objective, you know what's the factor and also the levels of factor that will affect the objective within your process. Next, you need to design and conduct the experiment. So design experiment, meaning that you have to choose what kind of experimentation approach that you want to adopt. It can be one factor at a time approach. It can be full factorial. It can be fractional factorial. It can be response-based methodology methods. So you have to identify what method you want to choose. We're going to go through, I think, two or three methods after this, and then that should give some idea to you on what the methods and how you choose which method for your particular experimentation. Once you design your experiment, then these experimental design, once you design the experiment, you would know how many experimentations you're going to run, what are the individual setting that you have to run for each individual experiments. So so usually you can design this kind of experiments using software. For example, you can, if you have a Minitab, so Minitab has modules on design of experiment. You can run, you can choose full factorial, fractional factorial, RSM, so on and so forth. Similar if you have a design expert software, or if you have a JMP software, jump software. Right? So usually you can just design your experimentations and actually analyze your experiment data using software. So it will ease the effort taken to design the experiment and also analyze the experiment. Once you design the experiment and you know how many runs of experiment you have to do, what are the setting for each experimental run, then conduct the experiment and then collect data and you analyze the data. That's it. You know. So once you're done with it, then the next step, and which is the final step, you need to validate and implement. So once you analyze your data here, then basically you're going to know what's the optimal setting to achieve the objective that you set for that particular experiment. So you would know what is the temperature level, what is number of eggs, so on and so forth, to achieve the maximum softness of your bread, for example, right? So once you get the setting, what you do, you need to validate that particular setting. So so you run validation run, and then compare that validation run result uh, with the predicted result that you can get. And the predicted result you can obtain after you do some data analysis here. Then basically you can even come up with a mathematical model to relate the input parameters, which is factor, to the output response, which is your objective. For example, you can come up with the mathematical model, usually it's polynomial model, mathematical model, that tells you how temperature change would affect the softness of the bread in mathematical form, and we call it empirical mathematical model, right? So you what you do is you run validations and compare your result with the predicted value based on your analysis. Once is validated, then basically you can implement the process change to optimize your process, right? So basically these are very basic step, uh, uh, two experimentations that you have to take, and even though there are only four steps, but the preparation stage here actually takes some times for you, because especially in terms of identifying factors and levels, you have to do literature review, you have to talk to experts to identify, what window of experimentations that you should choose, and what are the factors that could influence the objective. Okay. Okay, let's look at one factor at the time examples. So this is experimentations with retrospect using the one factor at a time example with respect to the gas mileage they can get from a car. So the problem is current gas mileage of our car is 23 miles per gallon. You want it to be 30 miles per gallon, but what is the best we can get? So basically, this for this experiment, you want to maximize the miles per gallon they can get out of a car. So this is maximization problem, right? So basically, so you need to understand what's the objective. The objective is to maximize the miles per gallon of a car, and basically, what might do the following. We might do the following to maximize the miles per gallon of the car. Change brand gas, change octane rating, drive slower, tune up car, wash and wax car, buy new tires, change your tire pressure. So these are factors. So these are examples of the factors. So these are the factors that could influence the miles per gallon performance of a car. So basically now you have to look at this particular scenario and come up with objective just now. So your objective is maximizations of the miles per gallon of the car, and you have to look at the what do you call it, the factors that might affecting it. So these are the factors that might affect it. Okay. Okay. So basically, from the examples, we have some potential factors that we have listed to investigate. And this factor, whenever you select this factor, it can be either continuous or discrete. Continuous means that the factor can be expressed in terms of 1, 2, 3, or 1.1, 1.2, 1.3, so on and so forth. It can be also discrete. Discrete means that, for example, if brand of gas, Shell, Mobile, Petronas, Amco. So those are brand of gas. So it's discrete. You cannot express it with regards to continuous number. Right? uh, octane rating can be continuous, driving speed continuous, tire discrete, so this is talking about type of tire, is discrete, but when we talk about tire pressure is continuous. So these are some of the factors that we have considered just now. And again, you have to remember that the factors can be discrete and can be continuous. Some terminology, just to reflect on what we talked about just now in terms of factor and levels. So basically the terminology: factor levels, main effect levels, uh, the value or setting of the variable being manipulated or being changed, right? So for example, is if you're talking about brand of gas, then Shell and Tesco. So your factor would be brand of gas. The level would be Shell and Tesco. Right? Example. The other example is the factor is speed, right? Driving speed, and the levels is 55 and 60, let's say, kilometer per hour or miles per hour, right? And another example is levels of octane. So level of octane can be level of octane itself. Octane itself is the factor, but the level for the octane would be 85 or 90. So basically, you have to understand and you have to identify the factors. The factors can be continuous or discrete, and you have also to identify the level of the factor. So if the factor is continuous, then it must be expressed with numbers. If it's discrete, then it can be expressed by brand, so on and so forth. Okay, okay, let's look at the examples of running this experiment using one factor at a time examples. For example, so again, just now we say that the current gas mileage that you can get out of the car is 23 miles per gallon. So every 1 gallon you can get only 23 miles. So you want to maximize it, right? So basically, if you run this experiment selecting three factors, which are speed, octane level, and tire pressure, that basically if you plan to run an experiment one factor at a time, so this is how you're going to do it. So first you need to what you need to do is basically you need to fix the rest of the factor, for example speed, right? So we have 55 So the level is 55 and 60. So those are the level that you choose. The octane levels that you want to choose to evaluate is 85 and 90. And tire pressure is 30 and 35, where 55, 85, and 30 is the baseline number. And with 85, with the speed of 55, octane of 85 and tire pressure of 30, what you get is basically the miles per hour of 23, right? So this is the baseline. So if you conduct an experiment using one factor at a time, so first what you do is you change the speed from 55 to 60, right? And then the rest of the setting will be the same as the baseline setting. So you run 60 speed, octane 85, tire pressure 30, and you get your result. And your result, for example, in this particular case, you get 24 miles per gallon. So you improve the miles per gallon by 1 miles per gallon. Then you run second experiment where you set the rest of the setting same as a baseline except for octane. So you increase the octane to 90, right? So you run it, you get 22 miles per gallon. And then you want to change the tire pressure from 30 to 35. You change 30 to 35 tire pressure whilst maintaining speed and octane at the baseline level. So you run it and you get the result of 20 miles per gallon. So based on this, what's your conclusions? Your conclusion might be you saying that, well, the best setting out of this particular experiment is actually if I set my speed at 60 miles per hour, octane at 85, and tire pressure at 30 psi. And out of that, I can improve my miles per gallon of the car to 24. So it's improvement of 1 miles per gallon. Right? So that's how we might explain the result, right? So, but how many more runs would you need to figure out the best combination of variables? But if you look at this, right, there are many other combination of variables that you have not run. You don't know what might happen if you set, let's say, for example, speed at 60, octane at 90, tire pressure at 30. You don't have that data, right? So if you want to repeat those experiments, you have to run a whole set of experimentations. Right? You set speed at 60, and then you change the octane at 90, tire pressure at 30. Then you have another setting where you have a speed at 60, octane at 90, and tire pressure at 35, so on and so forth. So uh, if if there were more variables, how many runs would it take you to get optimized solutions? So basically, you need to run many more experimentations um, uh, to get the full picture of what's going to happen. Right? What if there's a specific combination of two or more variables that leads to the best miles per gallon? So what if there's a specific combination of two or more variables that lead to the best miles per gallon? So basically, if there are other than this, if there are other combinations of settings that leads to the best miles per gallon performance, then if I run my experiment based on this only, then I'm going to lose that opportunity of improving the miles per gallon's performance of that particular car. So this is why if you have more than one factors, if you run one factor of a time experimentation, you might be missing the optimum condition. You might be missing the optimum condition, or you might have to run a whole bunch of experimentations, much more experimentation, in order for you to identify the optimum conditions. Optimum condition. So this is to give you scenario where you should not run one factor at a time experiment if you have more than one factors. Okay. So using the same examples, let's compare what would it be if you run this experiment using full factorial design of experiment. So just now, when we run the one factor at a time, so is the result that we got is the one that is shaded in yellow. So this run, and this particular run. So in order for you to turn the one factor at a time experimentation that we did just now to a full factorial design is basically to add one, two, three, four more runs. What you have to do is just add four more runs. When you set up your experimentations, depending on number of factors and levels, when you use certain software, either Design Expert, Minitab, so on and so forth, then it will tell you number of runs, number of experimentations that you need to run. So if you turn this particular case study into full factorial design experiment, then what the number of run would be 8 runs. You have to run 8 experimental runs. So compared to one factor at a time just now, we have to add another 4 runs, as shown here in white. 1, 2, 3, 4. So if you run the additional run, you might get a data that you didn't see just now. For example, you won't know about this experimental result where you have a 60 speed of 60 mp miles per hour, octane of 90, anti pressure of 30, resulted in miles per gallon performance of 28. And if you run at 60, 85, 35, you get 21, so on and so forth. So now, what conclusion do you make? So now, just now, when you just run one fact at a time, you miss these runs in white. So you make a conclusions. You might make conclusions that the maximum miles per gallon performance you can get out of the car is basically 24. So you are missing this result, this data. So with additional data, when you turn the one factor at a time experiment into full factorial design of experiment and got this result, then basically you know that the optimum setting to maximize the miles per gallon's performance of the car should be speed of 60, octane level of 90, anti-pressure of 30 psi. So this actually gives you some idea on the difference between one factor at a time versus this full factorial design of experiment in terms of informations that you gathered from the experiment. So again, if you have more than one factors to evaluate, don't use one factor at a time methods. Use design of experiment, either full factorial, RSM, or even fractional factorial methods. Okay, before we go into a detail of how to conduct a design of experiment approach, basically there are a few terminology that we need to understand, and some of this terminology we have covered just now, but just to re-emphasize the some of this terminology. So the first thing is called response. So response is a process characteristics that is measurable. So for example, just now in the example that we did on the miles per gallon performance, the response is basically miles per gallon performance. And this process characteristics must be measurable, means that you can measure it. You can put numbers to it, meaning that, like miles per gallon, yes, I can put number 23, 24, 25 miles per gallon. So process characteristics that can be measured is measurable. So a product that is measurable, the response is generally a y. So usually if you come up with an equation, y equals to something x plus something x plus something x, then basically the response is the y, in the equation, in the model. So example is a release, gloss, opacity, adhesive coating weight. So these are basically uh, some of examples of a process characteristics, and that can be measured. What about the examples that we used much earlier in baking bread, right? So we said softness. So is softness measurable? Softness might be measurable, might not be measurable, depends on how you gauge it, right? So you can have an expert in tasting the bread, and he will have a rating from 0 to 10 on the softness of the bread. So when he tastes the bread, he said that he can measure the bread softness with regards to that particular rating, 0 to 10. So if you can turn something abstract like maybe softness, taste, into something numerical value with regards to rating, then you can use that process characteristic as a response. But for example, if you want your response to be example microstructure, a microstructure of a grain, right? So if you cannot turn that particular output, for example, microstructure of a grid, into numbers, then that cannot be a response. So response must be something that's measurable, can be quantifiable. So if something is abstract, you can use some scale to translate the abstract of the measurement into numerical values, then you can use it. If not, then you cannot use that as a response. Okay. So that's a response. Second is a factor. So factor is process variables being investigated, is generally known as X. So we have talked about this quite in quite length just now. So in the examples of baking bread, so this factor would be temperature, number of eggs, so on and so forth, right? In the example, in the case study that we did on the one factor at a time. So you're talking about, speed, you're talking about octane level and tire pressure. So those are factors, right? So levels, again, we have talked about levels before. So for example, temperature will be 100, 150 Fahrenheit, so on and so forth. So it's a values of setting at which a factor is evaluated. And the other terminology, the other words that you need to understand is called interaction. Interaction. So you'll hear this when you deal with the design experiment, interaction factor, so on and so forth. So interaction, by definition, is the failure of one factor to produce the same effect on the response at different levels of another factor. So interactions, looking at interaction of two factors, right? So if there exists interactions between two factors, then basically this will happen. uh, as you said, the failure of one factor to produce the same effect of the response at different level of another factors. So for example, if you want to take the factor is the response is a taste, right? So you're talking about the temperature from 100 to 150. So baking temperature 100 to 150, and number of eggs is 1 and 2, right? So what this says is failure of one factor to produce the same effect on the response at different level of another factor. Let's say, for example, if you increase the egg number of egg from zero, from 1 to 2, then the softness of the bread will improve, right? So as the number of egg increase, softness increase. But that effect only true for, let's say, for example, at 100 degrees Celsius of baking, right? But so at 100 degrees Celsius of baking, as you increase number of egg, the softness of the egg increase. Okay? But you found out that at 150 degrees Celsius, then as you increase the number of egg, the softness decrease, right? So if that happen, then basically you can say that there is strong interactions happening in the process, where you have to look at that at a specific level of one factor to identify what is the optimum level of another factors, right? So that's the examples of interaction. So when that happen, then basically the optimum conditions of that particular process need to be determined based on the interaction factors. Okay, we're going to talk a bit more on this thing, and also we're going to look at some examples. So after looking at some examples, hopefully it will be quite clear to you. Okay, okay, let's look at the full factorial design and terminology. So we are focusing on full factorial design of experiment. So in the full factorial design of experiment, you can actually calculate number of experiment equals to L to the power of F, where L is levels and F is factor. For example, if you're talking about the example that we had just now in baking bread, L is the level. So if you have a if your factor, if you have two factors, then you put two factors have F here as two, number two, and L is level for each of the factors. So for example, if I conducted an experiment in baking just now, I have, let's say for example, three factors: temperature, number of eggs, and baking time. So I have three factors that I consider. So this F will be 3, right? And each factor I'm going to evaluate at two different levels: temperature at 150 to 180 degrees Celsius, number of egg 1 and 2, and baking time 30 minutes to 40 minutes. So L become 2. So then for that particular examples, I have three factors and two levels. Then number of experiment I have to run is 8, 2 to the power of 3. So example, if 2 to the power of 2 full factorial design consists of two factors evaluated at two levels. So number of experiment is 2 times 2, which is 4. Okay. Okay, so in terms of coding, so whenever you have experimental metrics, sometimes they give it to you in form of coding. So you have trial or experimental 1, 2, 3, 4. You have 4 runs altogether, and this is basically factors that you have to run. So the first experiment, you're going to run factor 1 at minus, factor 2 at minus. So what does this minus and plus means? So the coding basically is, if it's minus, then it's low level of a factor. If it's plus, then it's high level of a factor. For example, if you're talking about a factor of a temperature, so if temperature is a factor, and you're going to evaluate it at two different levels, 150 degrees Celsius and 180 degrees Celsius. Then 180 degrees Celsius is minus, then 180 degrees Celsius is plus. So this is the low level, and the plus is referring to high level. So basically, when you decide that you're going to run a full factorial design of experiment, you key in your two factors, factor 1, factor 2, and at each factor two levels, level 1 and level low and high levels in the design expert or Minitab software or jump software. Then basically it will give you this experimental metrics table, right? And it will tell you the first experimental run that you're going to run basically is going to be factor 1 at low level, factor 2 at low level. So you run this experiment and you get a result, right? So second run, basically it tells you to run factor 1 at plus, factor 2 at minus. So you run factor 1 at high level, factor 2 at low level, and you run experiment 2, run number 2, and then you get a result and you collect your data. 3 and 4 similar to it. So basically at this stage, basically you have designed your experiment by knowing what is your factor, what levels you want to evaluate, and what kind of design of experimental methods you're going to choose basically you key in all those things inside the software, and it will give you this experimental matrix, and this experimental matrix will tell you what experiment to run and what setting to run for that particular experiment. For example, if you're running two factors and two level, you have four experimental runs, one, two, three, four, and these are the setting for each of the experimental run. So it's very systematic way of executing your experiment if you use a design of experiment, right? So once you collect data, then you can analyze it. And basically for the analysis, I'm going to explain to you an examples of doing a simple analysis, but you can do more in-depth analysis with the software. And by all means, the software is out there, it's available. You need to understand the concept, the theory, the approach, but the nitty and gritty detail of analyzing, you need to understand the basic concept, but the nitty gritty detail of mathematical analysis of it, basically let the software do it for you. Okay, once you run the experiment and you collect your data, let's say for example your experiment is on the baking bread, right? So you run experiment, you collect the softness of the data, so on. So then you have to analyze your data. So let's look at the data analysis and terminology a bit. So the first thing is main effect. So main effect. So when people say main effect, it basically is the effect or impact of a factor on the response variable. So main effect indicates how a particular factor influence the output response, the response variable. For example, in the case of baking a bread, right? So you change your temperature from 150 to 180 degrees Celsius. So temperature is a factor. And you change it from 150 to 180 degrees Celsius. So main effect will tell you what is the effect or impact of the factor on the response variable. So as you change the factor, which is temperature, from 150 to 180 degrees Celsius, then what happened to the softness of the bread, right? So whenever you talk about main effect, is the impact or the effect of individual factor on the response variables. When you talk about the interaction effect, right? Interaction effect is the combined effect or impact of a factor on the response variable. So basically, when you do the analysis and you look at interaction effect, right? So the interaction effect is basically a combination of effect or impact on the factors on the response variable. So when you do data analysis, you're going to be given based on the result of the analysis will show you the main effect and also the interaction effect. So interaction effect is a combined effect or impact of factors on the response variable. For example, the combined effect of temperature versus and number of eggs, right, to the softness of the bread that you bake. So that's interaction effect. So after the analysis, you'll be given a set of data, and usually it's in the form of what do you call it, the significant effect of individual factor. So the effect of individual factor is called main effect. The effect of interaction factor is called interaction effect. If the interaction effect is much more significant compared to the main effect, then what you need to do is you need to use the result of the interaction effect to determine the optimum conditions of the optimum setting for that particular process. Right? So note, the effect of a given factor or interaction is calculated numerically. Effect is equals to average of high responses minus average of low responses. So basically, we're going to go through simple examples later on. We're going to look at what this means in a bit detail. So in design of experiment, you are not looking at a particular data analysis from from a particular run, experimental run, but you look at the combined run altogether. So that's why when you calculate the effect of certain parameters, you're looking at the average rather than individual response. I think once we go through the example, this will be quite clear to you. Okay? Let's look at these particular examples. This is a case study of screw parts manufacturing. So this is manufacturing of a screw. So you are a process engineer in a company manufacturing screw parts. You decided to optimize the process yield. So you decided to optimize the process yield, meaning that you want to maximize the process yield. Process yield is basically yield is equals to a number of good parts over number of inputs. Let's say, for example, if they say you process 100 screws, and after you're processing 100 screws, you have two defect, then the yield will be 98 over 100, meaning that it's 98%. So that's what process yield is. During process characterization, the team lists out 17 factors which may affect the yield through brainstorming. So to improve the yield, to optimize the yield, to maximize the yield, basically the group of the team do a brainstorming sessions. And based on that brainstorming session, they came up with 17 factors which may affect the yield, right? But based on engineering knowledge, the team determines two factors as the most likely contributors to defective parts. So as any given brainstorming sessions, you get ideas, you get many ideas, but you have to screen them. So basically, the team, based on engineering knowledge, the team determines that two factors as the most likely contributors to the defective parts. So they're going to evaluate only two factors out of 17 factors coming up from the brainstorming session. And these factors are lubricant type and spindle speed. So you have two factor, right? And each factor, they're going to evaluate it at two different levels. So if you look at it, lubricant type, the first factor is lubricant type. So this is categorical. This is category. It's not numerical. Spindle speed is numerical, continuous. So basically, there are two factors and two levels. So number of run will be 2 to the power of 2, 4 runs altogether. So the levels for the lubricant type will be sealant oil and pure oil. So that's when you have a categorical factor as such, right? So the low levels and high level is not referring to low grade and high grade, but it's referring to different type of lubricant, right? Spindle speed set at 2500 rpm revolution per minute, and 3000 rpm revolution per minute. So you can see the value. So low level at 2500, high level at 3000 rpm. So this is with respect to the value of minus and pluses. So as mentioned just now, with two levels and two factors, factor A and factor B at two levels, basically you're going to have four experimental runs. So experimental run 1, 2, 3, and 4. So the minus and pluses is responding to the factor that we have just now, uh, type of oil, and also the other one is RPM, the speed, right? And when you conduct the run, so what you do is you run the experimental run. Basically, you have a minus minus, low levels, and you get 80% yield. Run number 2 is plus for factor A, and factor B is minus. So this can be type of lubricant A. B is speed, middle speed, right? So you run all the experiment, you get all the data. So one thing over here, so this is experimental run 1, 2, 3, 4. This is the standard experimental run that you get from the standard factorial matrix, right? But when you conduct the experiment, the software usually will tell you the sequence of run that you should do. For example, this is the sequence of run. So number one, the first run you should conduct is basically experiment 2. The second run is experiment 4, the third run experiment 1, and the fourth run experiment 3. So the reason why this is being suggested by the software because the experiment were conducted in random order, because you need in any experiment is very important to randomize your experiment so that you don't have bias, right? So the way the software come up with these randomizations of the run is basically they have a random number generator in the software, and the random number generator will assign the number of the experiment that you should conduct, the sequence of experiment that you should conduct, right? So you should follow the suggested sequence of running order as per the software recommendation. So in this particular case, then you run the experiment 1, you run the first run, you run experiment 2, the second run, you run experiment 4, so on and so forth. Once you got it, then basically these are the data that you collected from the study. So based on that numbers, then basically you can actually put it in this matrix in terms of the result. So this is factor A, this is factor B. So again, factor A is lubricant type, factor B is the spindle speed just now. So at minus means that this is combination of level of factor A, level of factor B as specified before this, right? So the way the data is analyzed as shown here, basically this is just a copy of the data set of data that we got just now. So it is experiment 1, 2, 3, and 4, and these are basically the levels of it. And there's additional one column in here is called AB. So AB, so this A is a factor A. So if you want to look at the main effect A, then you're looking at this particular data, main effect B, and this is the interaction effect factors. So the way this signage is determined is basically by multiplying A and B, right? So minus times minus equals to plus, minus plus times minus equals to minus, and minus times plus equal to minus, and plus times plus equals to plus. That's how the signage for the AB is determined. So and this is the response yield. So the way to calculate the main effect, so the effect of A on the output responses on the yield, basically this. So if you average the pluses, so where's the pluses? So this is for A, this is plus, this is plus. So you have 85.25 plus 90 divided by 2. That's how you get an average. What you get is 87.863. Right? So average or minuses. So minus for A is at these two experiment 1 and 3. So you have 80 yield from this minus. For this particular run, you have 82. So 80 plus 82 divided by 2, you get 81. And the effect is basically the difference between the plus and the minus, average of the plus minus average of a minus. So 87.63 minus 81 is equal to 6.63. So that's how you get the effect, right? So again, for B, the same thing, the same procedure. So B, run experiment number 1 and experiment number 2 is minuses. Experiment number 3 and 4 are pluses. So the average of pluses is basically the summation, the average of these two runs. So 90 plus 82 divided by 2, you get 86. And the minuses is basically 80 plus 85.25 divided by 2, you get 82.63. And the effect is basically the difference between the average plus and minus, average minus. which is 86 minus 82.63, which is 3.38. Right? And again, for the interaction column, so the average of pluses is the first and also the fourth run. So 80 plus 90 divided by 2, you get 85. And the minus is basically 85.225 plus 82 divided by 2, you get 83.63. And the effect of the interaction is basically the difference between the two, which is 1.83. So this is how you calculate the main effect and interaction effect between A and B. So the if you look at it, so this tells you that, so if you take the plus as you change the level of factor A, right, from low to high, basically you're going to have the increase on the effect on the yield by 6.63. On factor B, so this is the type of oil. Factor B is spindle speed. As you change the spindle speed from low to high, you will increase the what do you call it, the yield by 3.38%. And the interactions, basically the interaction factor is 1.38%. 1.38%. So based on this, basically you can tell the effect of each parameter, each factors and interactions on the output response, which is yield. And from here you can see, you can tell already that factor A, which is type of lubricant, has much higher effect to the yield compared to B, which is middle speed and interaction. Okay. Okay, based on the effect calculation just now, basically we know which one is more important factors than others. But you can also present the data in graphical form. It's called a dot plot effect. So in the dot plot effects, basically from 0 to high number, low to high number. And then basically what you do is you put the value of each factor effect. For example, just now we have factor A, which is what, 6 plus 6 point something. The effect of factor A 6 point something. So I put it here. Factor B is equals to 3 point something, and factor the effect of interaction is a 1 point something. So as you put it in this graphical form, we call it dot plot effect. Then basically you can tell immediately which factor is the most significant factor, the second significant factor, and last significant factor. So for this particular case, A is the most significant factor compared to followed by B, and followed by the interaction of A and B. Another way of representing the data that we had just now, the result that we have just now in terms of graphical form, is called main effect plot. So this example is a main effect plot. So this is factor A, lubricant type. So at sealant oil, which is minus, pure oil is plus level. Then you can see as you change from sealant oil to pure oil, then basically the yield increased 87 from 81 to 87. And over here is the spindle speed. So as you change the spindle speed from 2500 to 3000 RPM, then the yield increased from 82.63 to 86%. So if you look at these two, you can look at the significant level of the main effect, looking at the slope of this particular curve, with these particular two lines, right? So for factor A, the slope is much more steeper compared to spindle speed slope, right? So this actually indicates that the change of factor A from minus to plus will result in more change in the yield compared to spindle speed. So because of that, you can see that lubricant type factor of the factor A, which is lubricant type, uh, has more significant impact to the yield compared to the spindle speed. So whenever you see a graphical result, the main effect graphical result, then the way you interpret it, basically, if there is no change, there is no change. If the slope of the line, as you change from minus to plus, is almost flat, meaning it shows indicates that there is no effect, meaning that the change in fact that particular factor does not affect the response. So if you see the slope, significant slope as you change of the line, as you change the factor from minus to plus, then it indicates that there's a strong effect, meaning that as you change the factor level from low to high, then the response also change significantly. So because of that, you're going to have a significant slope on that particular line. So this indicates strong effect for that particular factor. Okay, so the graphical effect for the interactions can also be plotted as such, as shown here. So if you look at how this is plotted, so in the x-axis, it will be one of the factor, and basically you're going to evaluate one of the factor. For in this case is factor 2, factor B, which is the spindle speed. So the x-axis is spindle speed from 2500 to 3000, right? And you're going to look at the effect of spindle speed change from 2500 to 3000 on sealant oil and also on pure oil. So basically the y-axis, the yield, the output response. So the other factors is basically sits on the different legend or different line. So in this case, basically, you want to look at the first line here, the blue line. You want to look at represent the change of the lubricant of the spindle speed from 2500 to 3000 on the sealant oil. So basically, when sealant oil is as mentioned just now, sealant oil is minus, right? And pure oil is plus for the level of the lubricant oil. So at the level of minus spindle, which is 2500, and minus sealant oil, minus lubricant oil, which is sealant oil, then you get around 80, yield of 80. And as the spindle speed increased, right, to 3000 for the sealant oil, then you get a yield of 83%. And you want to compare the same spindle speed, the same range of spindle speed to the pure oil, which is pure oil is level plus for the lubricant. So again, you plot another line for the pure oil at minus level of spindle speed. Then you get 85.25. And as the speed increase, then you get as the speed increase to 3000 with pure oil, then we get a yield of 90%. So if you look at it, as you increase the spindle speed from 2500 to the spindle speed of 3000, the rate of increase for the sealant oil and also pure oil, the rate of increase of yield for both sealant oil and pure oil as spindle speed increase about the same. So they're still about the same. So this indicates there is a minimum, there is not much of interaction effect that actually influence the yield, right? But if let's say, for example, if this particular plot is this pure oil is trending downwards like this, having a negative slope, then basically you can see as the change of spindle speed from low to high level, then the yield will have a opposite directions. If this pure oil line is actually negative slope. So if that's the case, then it indicates a strong interaction. But for this particular case, it indicates that the behavior of the yield, the output response yield, in terms of its trends, does not change as the spindle speed move from 2500 to 3000 for both pure oil and sealant oil. So this indicates that there's the interaction factor is not that strong, right? So the general way to interpret interaction effect is this. Now, if you see the line have a different slope, and if you have different slope, most often than not it will cross each other like this. This indicates a strong interaction. But if the slope of the curve basically is the same as shown here, and also shown in our example just now, indicates that there is no interactions happening for this particular case. So based on the data analysis that we did just now on the screw part manufacturing, what did we learn from that experiment? What type of lubricant should we use, and what spindle speed should we set to optimize the process? What should you do next? So basically, based on that particular experiment, then this is what you get. So you know that the most important factor the more important factor between the two, between lubricant type and spindle speed, is lubricant type. Lubricant type is more important factor compared to spindle speed. So you know that the thing that you need to control is basically what kind of oil you're using. So between the sealant oil and pure oil, you want to use pure oil. In terms of spindle speed, does the spindle speed affect the process? Yes, it's affect the yield, but at much less level, much less level compared to the lubricant type. So in order for you to optimize your setting, then basically you should set your setting at pure oil. Use pure oil and use spindle speed of 3000 to get your yield. And if you use that, then you should get your yield around 90%. So this is taking 3000, and for oil you should get a yield of 90%. So that answer the first and second question. So what should you do next? So what should you do next is basically you need to repeat this experiment, the finding, meaning that run your process at lubricant type of pure oil at spindle speed at 3000, and run it for a given amount of screw, and then recheck the yield. This is for confirmation. This is a validation. Make sure that you get the yield of 90% or something in that particular range, because again, there are variability in the process, so you might not get 90%, but you should get close to 90%. So once this particular optimized setting is verified, then basically you can change the process, manufacturing process per this requirement. So you run it pure oil with pure oil as lubricant, and spindle speed of 3000 RPM, and the expected yield should be around 90%. So this is case study number 2, which is a baking experiment. Basically, in this baking experiment, the two factor that you are looking at is temperature and time, and each factors are evaluated at two different level, which is minus and plus. For the temperature, is evaluated at 325 degree Fahrenheit and 350 degree Fahrenheit. And time is this is a baking time is evaluated at 12 minutes and 18 minutes. and these are the response. So there's response maybe in terms of the taste of the cake, and depends on whoever taste the cake, they give a marking marks on the taste of the cake. So you transform the taste into numerical number. Right? So we are not going to go through this, but I would like you to do it on your own. And if you have any questions doing it, please ask me during our online live online session. So these are the results from that particular experiment. So you get experiment, you get all this data, and then you get the average pluses, average minuses, average pluses effect for individual temperature, time, and also the interaction. So what you need to do is construct a graphical presentations of dot plot main effect, main uh, dot plot main effect, and also interaction effect. And then you have to answer this question: what is the most important variables and the optimum setting? What can you do? What can you do to further improve the taste of the cake? So based on this, then basically, I just want you to see, based on the data, see whether you can actually give some suggestions. They say, for example, if you want to further improve the taste of the cake, how do you do it? How do you do it? So please attempt this particular case study, and we have discussion. And if you have questions, we'll have discussion during our online live class session. As I mentioned just now, basically in this particular class, I'm going to give you some example. I'm going to show you some examples which I did, and the analysis, the basic analysis that's being done on the data. But those are not the only analysis that you can do. So there are more in-depth analytical analysis that can be done in the design of experiment approach. So there are a number of methods that are available to statistically quantify DOE results, and basically one of it is one of the important one is called ANOVA, analysis of variance. So if you run your experiment, design it and analyze it using software, either Design Expert or Minitab or Jump. Basically, they're going to do a further analysis, a more in-depth analysis compared to what we did just now. I will not cover the analysis in detail here, but I'm going to show you the analysis that you can get from the software and how to interpret it, so that you can actually internalize and appreciate the amount of data result and also interpretations that you can get out of this experimental analysis. Let's look at the sample of analytical analysis that can be done on this experiment approach using software. And for this particular case, I'm using Design Expert software. And the approach, the design of experimental approach that I used is called RSM, Response Surface Methodology. So basically, this is based on real case study of experiment that I myself conducted. So this particular experiment is on the optimizations of the process parameter for physical vapor deposition coating process. So this particular process actually put a layer of thin film coating on top of a substrate, and for this particular case, the substrate is tungsten carbide, and the coating is titanium aluminum nitride coating. So I studied three factors, which is sputtered power, bias voltage, and substrate temperature. and I'm going to evaluate it at two different levels and also at the center point. And because of that, then basically I have 20 runs, 20 experimental run that I have to do. And basically the response for this particular case is hardness. So I'm going to look at by changing the three factors: sputter power, bias voltage, and also substrate temperature. I want to look at the impact of those factors on the hardness of the coating, right? So basically that's the background information about the experiment that I conducted. So based on that, then basically, if you look at the last column, basically based on the run, basically I just jot down the result that I got. The result is in gigapascal. So this is a measurement of the hardness in gigapascal. So let's look at the analysis that can be done on this data using Design Expert. Same analysis can be done using any other software like Minitab or Jump. Right? So the first analysis that I can do basically is the sequential model sum of square analysis. And this analysis basically will suggest to you, so this is the beauty of the software, it will tell you what kind of model suitable for that particular data. So it will tell you the suggested model. So for this case is a quadratic model. So it tells me that I can actually use a quadratic model to explain the relationship between the input parameters, the three factors, and the output response, which is hardness. Right? And it will also show you the lack of fit test. So it actually suggested that I should use a quadratic model, and later on, if you go in depth with this particular methods, then you can explain what all this value means. I'm just going to show you the snapshot of the analysis that can be done using the software on the experimental design of experiment that I conducted. So this is the important one of the most important table that you get from the analysis, which is called ANOVA table. Right? So in the ANOVA table, it tells you which the factors are important significant factor. So this is factor the three factors: sputter power, bias voltage, and substrate temperature. And these are the interactions between A and B, A and C. So A refers to sputter power, B refers to bias voltage, and C refers to the substrate temperature. So it will show you the interactions between those parameters. And this is A2, AB2, and C2 is actually A square, B square, and C square. Is actually the quadratic functions of the factor, and also the interaction between A, B, and C. So this is basically the ANOVA table that you get from the analysis. And basically the software will do it for you, but you need to be able to interpret the result. So I'm just going to quickly show you what I got from here. So from here, basically, if you want to know whether the factor is significant or not, then you have to look at the p-value. Any p-value, the lower the p-value, the better it is. But for this particular case, I set 95% as the significant level, meaning that if I got a p-value of less than 0.02, 0.05, then that particular factor is significant. If not, then it's not significant. Right? But having a look at this, then basically I can improve the model a bit more, because there are a lot of not significant factors in here. For example, the interaction between B and C is not significant. So A and B is not significant, so on and so forth. So those insignificant factors, I can take it out to improve the model much better, right? So so from here, then basically I can generate the sum of the curve So this is again, this is the main effect plot. So if you remember the main effect plot, so this is for bias voltage, substrate temperature, and sputter power. So it shows you that as I increase I increase the bias voltage, what happened to the hardness? It will increase, right? So a substrate temperature, meaning if I increase the substrate temperature from low to high, there's no difference, right? But at the center, there is a curvature. There's curvature. Sputter power, if I increase the what do you call it, the sputter power, then basically the hardness will also increase. And but the curvature is upside. This is the curvature is downwards. So this is the main effect plot that I can get from the analysis, and it's all generated by the software itself. So these examples of interaction plot, for this case, is interaction between the sputter power and also substrate temperature. So you can see that if I so the red line is for the temperature, and the black line is for the red line is a temperature at 518 degrees, and the black line is temperature for the setting of 281 degrees, right? And the x-axis is sputter power. So looking at the graph only, just looking at the graph, you can see that the as you change the sputter power for the different level of substrate temperature, the slope is different. So this is sloping down and this is sloping up. So this indicates that there's a strong interaction between the two factors, right? So immediately from the graph, you can see there's a strong interaction between the two factors. And this is interaction between A and C. So you can see, look at ANOVA table. So interaction between A and C, you can see that the what do you call it, the p-value is a bit low, is quite low. So this is correspond to the ANOVA analysis. And you can also generate the surface modeling as such. So you can have a great what do you call it, graphics to explain the data. So in this case, is the x-axis is the sputter power, z-axis is bias voltage, and the y-axis is hardness. So you can see the behavior of hardness as sputter power and bias voltage changes. And you can actually develop the mathematical model. So this is what I mentioned just now. You can develop the mathematical model to explain the relationship between the output response and also the input factors that you evaluated. So all this can be done using the software, and all the analysis. Once you get the data and you crunch the number, for the analysis to be done with software, it will take you maybe about half an hour only. So it's very, very fast. It's not a tedious process. Okay, so before we stop, I just would like to share with you some tips of a good experimental planning. So aside from what we have covered just now, these are some of the tips. So when you talk about defining the objective, clearly define it. You have to define the objective very clearly. What that we don't know now, will we know when the experiment is completed? So you have to answer this. You have to ask these questions, to yourself. What we don't know now, and will we know when the experiment is complete? So for example, what we don't know now is basically maybe the optimum setting for the baking a bread, to get the softest bread possible. So after you run your experiment, then hopefully you know what's the setting. So you need to be very, very clear on what you want to achieve, right? Knowledge of the process is very important. Even though these are the tools is a good tool, but before you conduct your experiment, you need to understand your process. You need to understand the process very well. So you can do that either involve the process experts. So if you are not the process experts, then make sure that you engage with the process experts when you want to design the experiment for that particular process. Involve new set of eyes. So always nice if you talk to somebody else on your experimental plan, on the process, not only from your group but from external group. That's why this is important. It's important for you to actually do a very comprehensive literature review, because you want to look at the problem from different side, different angle, from new set of eyes. Right? Use process maps and FMEAs. If you have process maps of the that particular process maps, uh, which tells you what are the parameters, how the product are made, manufactured, so on and so forth, or the step, the important key parameters, and FMEA, failure mode effect analysis. If you have that for your process, then use it, because this actually contain very important information about the process itself. What the cause of failure, what the probable cause of failure, so on and so forth. So if you have it, these documents, then use it. Right? I think you should cover. You will or have covered FMEA in the previous class. Right? Determine number of measurement needed for each response. So you have to understand and figure out and determine the number of for each response. For example, if the first experiment is basically the first experiment that you run for experiment one, if you want to measure the softness of the bread, how many times should you do it, right, to get a good value. So basically, this is something to do with ensuring that the data that you get is actually representing a good data, a good data. So this has something to do with application and repetition, right? So you have to determine, every single measurement that you do is an average of how many data points, and determinations of average of how many data points depends on your knowledge about the process itself, right? Another tips, I think this is the last tip. Basically, when you selecting selection of the factors and level, again, this is very important to use your process knowledge, meaning that you need to have a good knowledge about the process itself. And when you select the setting factor levels, you need to set the factor levels wide enough to detect active effect. So, for example, if you want to select the level for the temperature of baking a cake, uh, you don't want to select from, let's say, for example, 150 to 151 degrees Celsius, because that the change in level might not produce any difference in terms of the softness of the cake itself. So this is where you need to really understand the process and read literature, do literature reviews on that particular process to understand what are the effective range of parameters for a specific factor that you should set. Okay. Further apart, then normally feel comfortable with. So you want to set the factor levels further apart than feel comfortable. For example, in the literature review, it stated that the evaluation prior to yours, look at the temperature level at 150 to 180 degrees Celsius. So maybe you want to open it up a bit, from 140 to 100 and 100 and 100 and 100 and maybe 85 degrees, 190 degrees Celsius, but not so far that response has no value. So, but you don't want to open up the window of the levels for each factor too big, such that you're operating at the value that doesn't make sense scientifically. For example, if I want to bake a cake, I want to open up from 150 to, let's say, 300 degrees Celsius. It doesn't make sense, because at 300 degrees Celsius will burn the bread. So again, the process knowledge is very important. What is the workable levels need to be determined by the process expert, and also from literature. Right? Examine all factor level combination for hazard and useless results. So again, you have to look at combination of examine all the factor levels combination for hazards and useless results. So example I mentioned just now, if let's say you want to open up the factor, up to let's say 300 degrees Celsius, doesn't make any sense at all, because the result that you're going to get is useless because your bread is going to burn. So having that process knowledge, then you know what's the limitation in terms of the how wide the process level should be, right? So again, setting factor levels, you have is must be wide enough to detect active effect, but it cannot be too wide, such that the result will be knowingly bad results, right? You don't want to do that. So basically, those are the that's the end of the chapter on design of experiment. Basically, again, to recap, if you have experimental experiment that you want to run to evaluate multiple factors on output response, then basically you should not use one factor at a time. You should start thinking about using design of experimental methods, either full factorial, a fractional factorial, or even RSM to do that. And when you run your experiment, please by all means use a software, the assistant of the software, to do that. That will ease the data analysis and ease the interpretations of the data that you get from the experiment. So that's the end of this chapter.